The theory behind artificial intelligence is just incredibly clean. We see these sleek, elegant diagrams of nodes and connections, and honestly, it looks absolutely flawless on paper. But here's the messy reality. If you sit down right now to build a deep neural network, wire the whole thing up, and hit go, it is almost certainly going to fail on the very first try. I mean, it might just sit there and do absolutely nothing, it might spit out total garbage, or the math might literally just blow up in your face. But why is that? Why does this beautifully theoretical system completely break down the second we put it into practice without some very specific under-the-hood tweaks? Well, welcome to this explainer. Today, we're prying open the black box. You can really think of this as your personal survival guide for fixing, tuning, and ultimately mastering a high-performance deep learning engine. We're going to dig into the exact mathematical cleverness you need to take an AI that is completely failing and transform it into a state-of-the-art model. It's like a giant puzzle, and we're putting the pieces together. So here is our quick checklist of the 4 tools we need to get a broken network up and running. First, how networks actually learn. Second, fixing vanishing gradients. Third, taming exploding gradients. And finally, speeding up gradient descent.
All right, let's dive right into section 1, how neural networks learn, the engine of learning. Because to understand how a network breaks, we absolutely have to understand its core engine first, which is backpropagation. So backpropagation is essentially the network's way of auditing itself. Just imagine a network trying to guess a picture of a cat and getting it completely hilariously wrong. Using the chain rule, it basically works backward, layer by layer, to trace exactly which weights caused that error. It's kind of like a backward game of telephone. Now, don't worry, we are absolutely skipping the grueling matrix calculus today. You're welcome. But the crucial takeaway here is that this backward pass assigns the blame. It shows the network exactly how it needs to adjust its connections for the next round. And that brings us to this incredibly elegant 4-step loop of training. Step 1, we forward propagate. We feed the data in and the network makes a guess. Step 2, we compute the loss, which just means measuring exactly how wrong that guess was. Step 3, we back propagate that error, sending the signal backward to find out who's to blame. And finally, step 4, we update the weights, tweaking all those little dials so the network is just a tiny bit smarter for the next round. You repeat that loop millions of times, and boom, you've got a trained AI. But, as you might guess, this whole process is incredibly calculation heavy. To keep this from taking a literal eternity, engineers use a brilliant computational hack called caching. See, the backward pass actually needs a lot of the exact same numbers that the network just calculated during the forward pass. So, rather than doing the math all over again, the network simply saves or caches those variables in memory. When it's time to work backward, it already has the answers on hand. It's trading just a little bit of computer memory for a massive, massive boost in speed. Okay, but what happens when that vital learning signal completely dies out on its way backward? That brings us to section 2, fixing vanishing gradients and keeping the signal alive. This is a massive roadblock that actually plagued AI researchers for years. Now, what's really interesting here is the geometry. Every single neuron has what's called an activation function that decides how to pass information forward. For a really long time, the classic go-to choice was the sigmoid function, which has this smooth S-curve shape. The problem? Well, if inputs get too extreme, the edges of that curve flatten completely out. The slope becomes 0. And as we all know, multiplying by 0 just kills the math. The learning signal vanishes. But the modern fix? Switching to the ReLU function. Because ReLU has this sharp angle, if a number is positive, it just passes the math straight through with a slope of 1. The signal survives, and the network learns cleanly. It's a real game changer. Now, you might be wondering, why do we even need these complicated functions in the first place? Why not just pass the math through normally and save the headache? Well, the source material gives us this fantastic quote. If you don't choose activation functions, it's going to be equivalent to a linear regression. Basically, without these specific mathematical curves bending and twisting the data, it doesn't matter if your AI is 100 layers deep. The whole thing mathematically collapses into a basic flat statistical line. These functions are the literal source of the network's ability to actually understand complex reality. All right, so we fixed the dying signal, but what if we run into the exact opposite problem? Let's move to section 3, taming exploding gradients, controlling the chaos. If vanishing gradients happen when our numbers shrink down to 0, exploding gradients are what happens when our numbers compound and multiply straight towards infinity. Just imagine a 10-layer network where every weight is just slightly bigger than 1, say 1.5.
As you multiply 1.5 by itself across layer after layer after layer, those numbers exponentially balloon. Suddenly, your network is trying to process astronomically huge numbers. The math literally overflows the computer's memory, and bam, catastrophic failure.
And one massive cause of this chaos? Throwing raw, unnormalized data straight at your network. I want you to imagine the network's learning journey as a hiker trying to walk down into a deep topographical valley to find the absolute lowest point. If your data is unnormalized, meaning the numbers are just all over the place, that valley is incredibly skewed and stretched out. The network is going to bounce erratically side to side in these frustrating zigzags, taking forever to reach the bottom. But if we normalize the data, centering everything neatly around zero, that topographical valley becomes perfectly round, like a smooth bowl. And that provides our network with a direct, steep, and highly efficient path straight down to the solution.
But hey, fixing the data isn't the whole story. We also have to fix how the network actually starts. If the starting weights are too big, they explode. Too small, and they vanish. So the absolute crucial point here is finding that perfect Goldilocks zone. And that is exactly where Xavier or Glorot initialization comes in. It's this brilliant technique that carefully sizes the starting weights of every single neuron based exactly on how many inputs are feeding into it. It scales the math so precisely that the signal stays perfectly balanced as it flows through the whole network. It's basically the ultimate setup for a successful training run. Okay, section 4. We now have a stable network that isn't going to die and it isn't going to explode. But training it sequentially on millions of images is still agonizingly slow. So let's talk about speeding up gradient descent and racing to the finish line. When it comes to how we look at our data, we've got two extreme options. We could use batch gradient descent, which looks at the entire dataset of, say, 1 million images all at once before making a single update. Now that gives us perfect, pinpoint accurate directions, but computing 1 million images just to take one tiny step, far too slow. On the exact opposite end of the spectrum, we have stochastic gradient descent. Here we look at just one single image, update the network, look at the next image, update again. It's lightning fast. But because it's reacting to just one image at a time, the learning path becomes incredibly noisy, chaotic, and erratic. So what's the industry standard solution? Well, we compromise. We use mini batch gradient descent. Instead of looking at 1 million images or just one single image, we look at small, manageable chunks, say 1,000 images at a time. It really is the ultimate trade-off. It's large enough to give the network highly accurate directions, but small enough that our hardware can process it incredibly fast. But even with mini batches, the path to the bottom of our Lost Valley isn't always smooth sailing. Imagine you're physically sliding down a really bumpy, uneven hill. How on earth do we keep our network from getting stuck in the ruts or wildly overcorrecting every single time it hits a bump? Well, we add momentum. The algorithm actually looks at the average of its past updates to decide its current move. The source material compares this to a heavy rocket, which I just love. A rocket has mass, right? It can't just wildly zigzag left and right in an instant. By applying momentum, the network dampens out those wild side-to-side oscillations, taking the average path, which accelerates it rapidly in a straight line toward the goal. It literally just blasts through the noise. And so, we kind of come back to exactly where we started. When you hear about deep learning and AI out in the world, it is so often framed as magic. But as you've seen in this explainer today, a working neural network is anything but a magical black box. It's a beautifully orchestrated engine of optimization. It requires caching to save memory, specific mathematical curves like ReLU to keep signals alive, precise initializations to prevent explosive chaos, and clever physics-inspired momentum to blast down the optimal path. So the next time you see a massive AI model do something incredible, you'll know exactly the toolkit keeping that unbelievable engine running. Thanks for joining me today, and keep questioning how the magic works.